July 16, 1945. The New Mexico desert, an hour before dawn. 100 scientists lie flat on the ground, backs turned, welding goggles pressed to their faces. Then the sky ignites. For a fraction of a second, the desert floor is lit up brighter than the sun at noon. And for 100 miles around, night becomes day. This is the moment the atomic age begins. But this story doesn't start in a desert. It starts 200 years earlier, with a jar of yellow paint. The deadliest substance ever made by human hands did not begin in a weapons lab. It began as a coloring agent, a way to make glass glow a pretty shade of yellow-green. For 100 years, people ate off it, drank from it, and had no idea what it truly was. The story of how that pigment became a bomb isn't really a story about physics. It's a story about accidents, about refugees who saw danger before anyone else would listen, about a woman who solved the equation that changed the world and got nothing for it. This is how a paint color became Trinity. Berlin, 1789. A chemist named Martin Klaproth was studying a heavy black rock that miners called pitchblende. Worthless stuff, they thought. A nuisance dug out of silver mines and thrown aside. Klaproth dissolved it in acid and watched it turn a brilliant yellow. It matched no known element. He'd found something new, and in the fashion of the day, he named it after the newest thing in the sky. The planet Uranus, discovered just 8 years before. Uranium. For the next 100 years, that's all it was. A pigment. Glassmakers used it to tint bottles and tableware a glowing yellow-green. Nobody thought to ask what else it might do. Nobody had any reason to. A century later, in Paris, a physicist named Henri Becquerel was chasing a completely different idea. He believed sunlight might trigger a hidden kind of ray inside certain glowing minerals, including uranium salts. His plan was simple. Leave the crystals in strong sun, then see if they fogged a photographic plate wrapped in black paper. But Paris stayed gray. Day after day, no sun. Frustrated, Becquerel gave up, wrapped everything in cloth, and shoved it in a drawer to wait out the weather. When he finally developed that plate anyway, almost as an afterthought, he found a perfect image burned into it, with no sunlight involved at all. The uranium had been producing its own energy the entire time. Radioactivity wasn't discovered by a brilliant experiment. It was discovered because the weather in Paris refused to cooperate. Marie and Pierre Curie took it from there, working in a leaking shed in Paris that one visitor compared to a stable. They spent years boiling down tons of raw pitchblende ore by hand, hunting for whatever was hiding inside it. From all that ore, they extracted barely 1/10 of a gram of a new element, radium. Marie loved walking into the shed at night just to watch the glass tubes glow, faint blue-green light, like something alive. She carried vials of it in her coat pocket. She kept samples in her desk drawer. Nobody yet understood the cost of that intimacy. Her lab notebooks are still radioactive today. They sit in lead-lined boxes in a French archive, and anyone who wants to read them has to sign a waiver and put on protective gear first. A few years later, Ernest Rutherford fired particles at a sheet of gold foil, expecting them to sail straight through, and a few bounced back, like a cannon shell ricocheting off tissue paper. That's how the world learned every atom hides a tiny, dense core at its center. By 1933, a Hungarian physicist named Leo Szilard had already fled Berlin. He kept 2 suitcases packed at all times, a habit of a man who'd learned to trust his instincts about danger. In London, he read a newspaper account of a leading scientist dismissing the idea of atomic energy as pure fantasy. Irritated, Szilard was crossing a street near Southampton Row when the idea hit him whole, mid-stride, at a traffic light. If one atom split and released 2 neutrons, and each of those split 2 more, you'd get a chain reaction, a cascade of energy multiplying on itself. He patented the idea a year later. Then, worried what a hostile government might do with it, he handed the patent to the British Admiralty and asked them to keep it secret. In Berlin, chemist Otto Hahn kept getting a result that made no sense. Bombard uranium with neutrons, and you find barium, an element half its size, left behind. He wrote to his longtime research partner, Lisa Meitner, for help. But Meitner was no longer in Berlin. Weeks earlier, with Austria's protection gone and Nazi racial laws closing in, she'd fled the country with 2 small suitcases, uncertain the border guards would even let her through. That Christmas, in a Swedish village, her nephew skied out to visit her. The 2 of them walked in the snow, him on skis, her on foot, trying to keep up, until they stopped at a tree stump to work through Han's impossible numbers. And there, in the snow, they solved it. The uranium nucleus wasn't decaying. It was splitting clean in 2, releasing enormous energy in the process. They gave the process a name borrowed from biology: fission. Hahn published the chemistry. Hahn alone won the Nobel Prize. Lisa Meitner, the physicist who did the calculation and named the phenomenon, received nothing. Word of fission spread through physics circles within weeks, and a small group of refugee scientists in America, Szilard among them, understood the danger before almost anyone else. If Germany, the country that had just discovered fission, built a bomb first, there might be no stopping it. So they wrote a letter and asked the most famous refugee of all, Albert Einstein, to sign it. The letter reached President Roosevelt in the fall of 1939. It warned of a phenomenon so new it barely had a name yet, one that could, in its own words, lead to the construction of bombs. It was refugees, again and again, who saw the danger first and forced the rest of the world to take it seriously. By 1942, the American, British, and German bomb projects were all buried under total secrecy, which turned out to be its own kind of announcement. A young Soviet physicist named Georgy Flerov, reading physics journals in his off hours from the front, noticed something odd. An entire field of research on nuclear fission had simply gone silent, all at once, across 3 countries. Scientists don't stop publishing on a hot topic unless someone tells them to. Flerov understood that the silence itself was the evidence. In April of 1942, he wrote directly to Stalin, "They're building it in secret, and we need to as well." Germany, meanwhile, had already given up. Its own physicists told their government a bomb would take too long and cost too much, and the project was quietly set aside. The country that discovered fission never built the weapon it made possible. Which brings us back to the desert. July 16, 1945, Alamogordo, New Mexico. A storm had rolled through overnight, delaying everything by an anxious 90 minutes. Observers on a distant mountain, exhausted from the all-night wait, nearly packed up and left in the last minutes before dawn, mistaking the coming flash for an ordinary sunrise. Then, at 5:29 in the morning, it came, a light brighter than the sun, turning the pitch-black desert into daylight for a fraction of a second, followed by heat that could be felt for miles, and then, tens of seconds later, a deep and rolling roar. One physicist who watched it said the crowd's reaction was awe rather than excitement, that everyone who saw it went away knowing they'd witnessed one of the great events in history. 200 years earlier, this element had been a paint color on a dinner plate. Now it was the most powerful weapon ever built by human hands, and the world would never look the same again.